one in the back from Eni, from Italy. Very interesting.
You have to wait before saying that is very interesting. I mean, this paper is an attempt of telling you how we in the industry try to apply all the ideas about hydrogen embrittlement. And this is only the beginning of a project.
That's the reason why it's interesting, because it's from industry.
Yes. And so the case is this one. We have trunk lines carrying sour fluid. So with a high percentage, about 5% of H2S and 5% of CO2. So this fluid is thought to be quite aggressive, and we also try to have no water. So we have a very little amount of water. If the water increases because the production of the wells is adding water, we stop some well to keep the water very low, something like 2% maximum. And also, we try to carry the oil quite fast so that the water is carried away and doesn't precipitate on the surface. So the point is that these pipelines have got some lamination, but we never had the feeling of those lamination. The pipelines were built in 2004, and we started to have some some evidence of lamination only 14 years after, or 12 years after, and nothing happened before. So now the problem is that what can we do? Because we have to change, of course, the pipeline with a better steel. But in the meanwhile, we have the necessity of producing the oil. So we have been trying to study the problem and see what can happen. Usually what we do for fitness for service, for life assessment of a pipeline, we do kind of different things like to make inspection, and the inspection are made with intelligent pigs. And also we try to apply models to make comparison between different runs of the pig and so on. But the problem is that when you make an inspection with the pig, you must select the kind of tool to get the information that we need. In this case, for instance, we had some, at the beginning we used this pig, which is a magnetic pig, and this one see very well the reduction in thickness, but doesn't see cracks. Instead, if we use ultrasonic, we can see cracks, but we cannot see very well the reduction in the wall thickness. So the point is that at the same time, the idea was, are those defects going to grow? And now the point is that lamination cannot grow. This kind of defects are embedded inside the metal, are fabrication defects. And they are there since the beginning. And usually they lay in a direction where the pressure inside the pipeline doesn't give a problem. There is no stress, unless they are sloping or they are arriving to the surface. So we cannot expect that the lamination grow. The lamination is a different material inside. At the other hand, we can imagine that some crack can start from lamination. Especially with hydrogen, you can have hydrogen accumulating inside and making blisters. So you have like a bubble with pressure inside, and that will start a kind of mechanic growth, maybe due to fatigue. If you have a change in pressure, which is normal in a pipeline, you have some fluctuation in pressure. So the point is that when we use an intelligent pig, are we going to be able to detect both cracks and lamination? And so which kind of pig do we have to select to be sure that we measure what we need to measure? Another point is that stress corrosion cracking. Now, stress corrosion cracking, I wrote, is unlikely to occur because the material has been selected as not susceptible to stress corrosion since the beginning because the fluid was sour. Now, the point is to measure, to be sure that material is not susceptible, we use the so-called NACE solution, which is 1 bar H2S. When we have a situation with higher H2S, like 5 bar, but also 10, 12 of H2S, are we sure that the material is still not susceptible? And also the NACE solution is anyway at a low pH and water solution. In this case, we don't have water. So H2S is a poison for the recombination of hydrogen. But if the water doesn't dissociate, probably we don't have atomic hydrogen. And so the effect of H2S can be much lower than what we think. While the problem of fatigue and sloping lamination is probably much more important, but there is no corrosion here because the water or the fluid doesn't reach the center of my pipeline. So this is our speculation. I don't know if they are all correct. Anyway, we could get a piece. It was quite difficult because to get pieces of metal from some country very far away, a piece of the removed damaged section, and we made, we made some measurement, manual measurement of with ultrasonic, and we saw, I hope you can see it, that there is a kind of shape of defect. The point is that for the pig, this defect was only one big defect. Instead, when we look at the same was with the manual measurement in the lab. But when we look at closer, we saw that there were many small defects, not one large defect only. And if you look at the different measurements, they are more or less similar. We saw it for the first time with a magnetic pig, which is not supposed to be precise in seeing lamination, but saw something. And more or less, yes, the width is smaller, but more or less was good. If we look at the ultrasonic pig, we see that one of the points is that the location is a little different, about 100 meters of difference from one and the other. This is because the pig is not so precise in measuring distances. So this is the point. But finally, when we removed the piece, we found that we were able to locate the defect. But the point is that there is some difference in the measurement. So when we make two different runs of the pig, maybe 6 months apart, and we see different measurement of this lamination, to my opinion, we don't see a growing lamination, which is almost impossible, but we see a different measurement due to the tool we use. So this is why we suggested to avoid to pass the pig, to make pig inspection too often, because during the pig inspection you cause fatigue, you cause fluctuation in the pressure, and that can be more dangerous than weight sometime. At the same time, we are trying now to make a kind of program in the lab that has started now. I don't have results anyway. Still, I don't have results. But we tried to locate better the defects. In a way, this is something that is correlating with the invited speech of this conference, because we have different tools now with respect to 20 or 30 years ago. And for instance, this X-ray tomography is something that is applied usually in our company to investigate the rocks, to see in the rocks if you can find oil. In this case, it's the opposite. So you find something like rocks, so small inclusion, which are of the same nature of rocks inside the metal. And this seems to be quite good in giving you an image of, this is a specimen that we have been studying to try to make the sample very close to the real defect and to see if we can get propagation in some way and understand if this propagation can be for stress corrosion cracking, for hydrogen embrittlement, or for fatigue and so on.
5 minutes remaining.
Yes, this, I'm almost finished. This is, for instance, they say that is manganese sulfide. Instead, in our case, with the SEM examination, with the modern SEM, which are very, very precise, we found that these defects are oxide of aluminum. And the same was here. In this case, you can see that there are oxide and double oxide, and here is the microstructure of the material, and there is no void, so no blisters. And this is why the people said, to our opinion, there is no hydrogen cracking. Now, there are so many mechanisms of hydrogen embrittlement that probably you can say we don't see a blister, but we don't know if there is hydrogen around because we need other tools. And another point is that we looked at the water accumulation in the pipeline, and we saw that it can accumulate only at the beginning of the pipeline due to the shape, but also due to the fact that the water is very little amount. And so if you start to accumulate a little bit here, you don't have any water to accumulate in the second part. And so this is more or less in agreement with what you see about corrosion. So you see corrosion only in the first part of the pipeline, and while the lamination are distributed because they depend on the fabrication of the steel. So we are organizing this project where we will try to make some monitoring of hydrogen. We will try to make some, we will make a test program, and we hope to have the possibility of understanding better how a real defect will propagate. And so the conclusion are that we have seen that the presence of lamination confirmed by inspection, but we need to be sure that this defect change their size and see if we can, with the correct inspection tool, discriminate between lamination and blister. And also, the point is that with an ultrasonic pig, we don't see anymore the small corrosion that we get from the small amount of water. And this is very important because hydrogen can be produced only if there is corrosion in the metal. So this is the point where we started this project. And thank you for your attention.
We have a time for one short question. Professor Baruch is first.
I'm sorry, it's a stupid question, but what exactly you mean by lamination? Are these the cracks that you showed, or
they are no cracks. They are
this banding of the
there is a kind of inclusion, which is after, how do you say, is when you make a lamination of the material, the steel, before making the steel is laminated before you make the pipeline. If there is a small inclusion or something, that will be
decreasing the thickness.
Yes, you decrease the thickness and you make a traction in the material,
Yeah.
so the small defect there will be very thin and very long. And
So
this is
that's,
why...
that's typically in metallurgy called banding of the microstructure.
Banding usually is the microstructure.
Okay, that's
in this case, it's a defect that shall not be present. Usually, in a good steel for pipelines, you don't find it.
Okay.
But if you have some problems during the fabrication, in some region of the pipeline, you get this kind of defects. They are defects which are not metallic, are kind of oxide or sulfide or similar.
So this long M&S.
And they get this very long and thin shape due to the way you make the pipeline. That can be either laminated, bended and welded, or like in this case, it is, I don't know the English word, you increase the size of, start from a bar, you make a hole in the bar, and with the tool you start to increase the bar, the pipeline.
Just one
Extrusion.
very short question.
It's extruded,
So you
yes.
have the problem of that ultrasonic erroneously measuring this lamination also as cracks. Is that?
Yes, the point is that the ultrasonic can see it, but you must have the correct inclination of the tool and also see very well a crack, for instance. But maybe doesn't see every time, you know, a pig, intelligent pig, I don't know if you are familiar with, is a kind of vehicle with a transducer over it. And now moving inside the pipeline, maybe is rotating a little, so doesn't make the measurement exactly in the same way each run. And so it's normal that you can find some small difference. The point is that when you see such difference, can you think that your lamination is larger, or simply that your measurement has been a little different? You have, and also in this case, especially you see so many different small defects, and the tool see it like one large. So it's also more difficult to understand what is the real defect.
Thank you very much for a very good explanation.